resume our discussion on logical clocks and causal ordering problems that we were looking at in the last class. So, let us go back to Lamport's logical clock. So, in that definition, each process I keeps a clock C I, and each event A in I is time stamped by C I A, the value of C I when A has occurred, and every time an event occurs and is time stamped, C I, the local clock, is incremented by 1 locally. And in addition, if A is a send message M from process I to process J, then the message M is time stamped with the timestamp of A, that is from I. So, C I A is the stamp on the message, and on receive of the message M, the process J recomputes its clock as max of its existing value of clock and 1 plus C I A. Okay. Now, we saw that this clock guarantees that if some event A has happened before event B, then C A is less than C B. Okay. And the problem was that it does not guarantee the reverse, that is C A less than C B does not imply that A happened before B. Now, there are cases which we shall see, particularly for ordering messages, that we also need to know the reverse, that whether given that C A is less than C B, we should be able to show that A has happened before B. And that is important because when we receive a message, we need to figure out whether there are other messages which were sent before this message or causally preceded by this message. Okay. Then those messages will have to be received before I receive this message. Okay. So, when I deliver the messages in order to the higher layers of the network, I should deliver them in order. So, to get around the problem of Lamport's clocks, we introduced the notion of vector clocks, where instead of storing a single scalar clock C I at each process P I, we store a vector C I. The vector has n dimensions, where n is the number of processes, and the update rules are as follows, that whenever there is an event at process I, then the clocks, the ith dimension of the clock C I is incremented. If A is a send of message M from I to J with vector timestamp T M, then on receiving M, we compute the process J computes C J K as max of C J K and T M K. So, whatever timestamp it receives on the message, it takes the max of that with its current value on each dimension k. Okay. Then we saw that this definition of timestamps has a partial order, and we can define things like equal, not equal, lesser equal, not lesser equal, etc. Right.
So, can you just explain this part again about the dimension, max, calculating a max value for every dimension?
Yeah. So, that means that suppose the message M is time stamped with okay, and suppose at this point the clock value was okay. So, now given that this message was received with clock 275 and given that its current clock value, that is, this is process j, let us say, and this is Pj, this is message m, and this is Tm. So, I recompute Cj as the dimension wise max of these. So, Cj is recomputed as 2, 7, 9. Is that clear? That is how the clocks are updated. Now, we will add one here. If you count the receive event as an event, then you will add 1 to the jth dimension of this clock, right? Beg your pardon?
Actually 289 at that point.
Provided that this is j is 2. Okay. That it will just increment the jth dimension. Now, see, which events you are counting in your clock is decided by your algorithm. Okay. Now, let us be very clear about this. This is a logical clock. So, we are talking about certain events of interest. So, it does not mean that everything that happens in the processes will increment the clock. So, suppose my domain of interest is only events of type A and type B, then I will increment the clocks only when events of type A and type B has occurred, right. So, later on we will see another protocol where only the send events are time stamped. Okay. So, there we will see that when receiving the message we will not increment the clock, receive events are not counted there, only send events are counted. There we were counting both the send and the receive. Okay. So, here if you count the receive event as an event, then the jth dimension of this vector will be incremented. So, suppose j is 3, then this is going to become 2, 7, 10. Is that clear? Right. Now, let us with vector clocks we have the desired relationship that A happened before B if and only if Ta less than Tb. So, we did not have if and only if previously. Okay. We only had that if A happened before B, then Ta less than Tb, but now the other direction is also true, that if Ta is less than Tb, then A happened before B. Okay. Now, so that means that events A and B are causally related if Ta is less than Tb or Tb is less than Ta, else they are concurrent. Now, remember that when you say that they are something is less than something, it has to be less in at least one dimension and less than or equal to in all other dimensions, right. Now, note that this is still not a total order, because you can still have values which are concurrent and therefore not ordered, there is no order between two timestamps. Okay. Right. Now, how are you convinced about this statement that if Ta is less than Tb, then A happened before B? How? What am I trying to say here? I am trying to say that suppose you have event E1 and event E1 was event E2 Okay. So, this is the time stamp of E1, this is the time stamp of E2. Okay. So, we know that from this, by comparing the two, we see that TE2 is less than TE1. From this, we want to conclude that now how do we know that? The rest are equal, but how do you know that there is a causal order between these two? Yeah, but it was less in Lamport's clock also. In Lamport's clock also, if you had CA as 5 and CB as 3, okay, we could say that B happened. Could we say that B happened before A? No, but here this 3 was smaller than 5.
Yeah, because if any message received from any other thing, then also this quality will remain.
See, let us be clear. What do we want to show? We want to show that if the vector, according to this comparison rule, if this is smaller than this, then there has to be a causal order between the events. Otherwise, they cannot have these stamps. In other words, they cannot be concurrent. Because of local increment. So, how could these two this happen?
Every time a event will occur, they will both get incremented.
They will both get in. Which will get incremented? Only the ith dimension will get incremented. If pi, there is an event in pi, then the ith dimension of the clock will get incremented, right. So, what can we say about these two? Can we say that they happened in the same process? We can. So, if they are in the same process, then there is a causal order between this, because they are not concurrent and this clock was incremented. Okay. Now, what you must think is, think of cases where there are two events which are occurring in different processes, right, and then one has a time stamp smaller than the other, and then try to establish that there has to be a causal order between the two. In other words, what I am asking you to do is consider the situation where in pi there is some event A which has taken place, okay, and what is the value of the timestamp here? Let us say that is CIA, where CIA is a vector. Okay. This is some process Pj, and here some event B has occurred, which has been timestamped with Cjb, and we are given that CIA is less than Cjb, given that I is saying prove that A happened before B. In other words, there has to be a causal sequence some kind of causal sequence from A to B, right, by virtue of which we can say that A happened before B. Is the question clear? Given that CIA is less than CJB, where Ci is a vector clock, CJB is a vector, and we want to show that A happened before B. Right? This we have to prove, otherwise we haven't really shown that vector clocks guarantee this fact, that whenever one vector clock is less than the other, then that event must have happened before the other one. Okay? If you get stuck, let me know. What we are going to look at here is the use of vector clocks in causal ordering of messages. So, what we want to do is, if send of M1 happened before the send of M2, then every recipient of both message M1 and M2 must deliver M1 before M2. This is the requirement, that if a message was sent before a message M2, and happened before means what? They are causally related, not incidentally that something was sent in real time before another, not that. We are talking about happened before relationship, which means that there is a causal relationship between the send of M1 and send of M2. Then every recipient of both M1 and M2 must deliver M1 before M2. Now, what do we mean by deliver? That is when the message is actually given to the application for processing. So, what we mean is that we have this node which is receiving, this node is receiving messages from the network. Okay. So, it is receiving some M1, it is receiving some M3, then it is receiving some M2. Okay. Now, after receiving these messages, the node will order them and then deliver it up the network stack in the proper order. So, it will deliver M1 first, then M2, then M3, even though M3 was received before M2. Okay. Now, by deliver we therefore mean that it is delivered to the upper layers of the network stack, not to any other node as such. Now, this is the protocol, this is one of the protocols which is used for causal ordering of messages, order the received messages based on their causal order. To broadcast M from process I, now this is a broadcast protocol first of all. So, every message is broadcast to all nodes, right. Now, when we talk about broadcast, it is actually, you can think of it as messages being sent individually to every node, right. So, it does not mean that all of them receive it at the same time. So, when A broadcasts a message, B may get it now, C may get it sometime later. Okay. But every message is actually sent to every other process. So, to broadcast M from process I, increment Ci I and timestamp M with the Ci I. Okay. Actually, timestamp should be with Ci only. Okay. The whole vector is used for the timestamp. Okay, just there is a mistake here. It should be Ci only. When j not equal to I receives M, j delays delivery of M until Cji is equal to Vtm I minus 1 and Cjk is greater than or equal to Vtm k for all k not equal to I. Okay. Now, let us understand what is the meaning, what we are doing here. The whole issue of delivering messages in order is to decide when to wait or hold back the delivery of a message, because there are other messages which happen before this message, but have not yet reached me. This is the main issue. If I have received two messages, I know which one has a smaller timestamp than the other, and I can always use that timestamp. So, that for that we do not have to go to vector clocks. Even Lamport's clock is sufficient. If you have all the messages with you and you want to deliver them in order, you just order them by the timestamps and then deliver them, right. So, that is not the issue of causal ordering, that can always be done based on any partial order given on the messages. But the need for vector clocks is because when we get a message, we have to realize whether there is any other message which was sent before this or not, right. Now, that is what this step does, that when j is not equal to I, which receives the message m, j will not deliver m until Cji is equal to Vtm I minus 1, okay, and Cjk is greater than or equal to Vtm k for all k not equal to I. Now, let us get this clear. So, if let us take an example, suppose I get a message which is time stamped when I get this message, let us say that the vector timestamp here, okay, now this is a message which is received from Pi, okay, and this is Pj, all right. Let us say Pi is P, let me just actually write P2 and this is let us say P3, okay, and let us say the current value here of the clock is 4, 2, 8. Okay. Note that in the P3 dimension this can never be more than what it has. In the P3 dimension, this is the process P3. So, its own local dimension will always be most updated, right. So, it can never happen that say this is 7 and this was 5 or something like that, that can never happen. Okay. The third dimension being its own dimension will always be up to date. Now, see what P3 sees is that its first dimension is 4, but this message shows that the first dimension is 5. So, that there must have been another message from P1 which it has not received. In other words, what this clock is counting is the number of messages that it has received from the P1, P2, P3, right. So, when it has 4 and this one is showing 5, that means that P1 has sent 5 messages, otherwise how did this dimension become 5? Now, we are only counting the sends, we are not counting receives. So, the timestamps are only counting sends. Remember that in the broadcast protocol, in the first step we increment the clock, local dimension of the clock, when we send the message, right. So, when this is 5, it means that P1 has sent 5 messages, this is 4 means P3 has received 4 of those, it still has not received one of them, right. And that message was sent before P2 made this send, okay, because P2 has recorded that this is 5. So, the send of that message, that fifth message by P1 precedes the sending of this message M by P2, okay. That is one thing. Now, compare the second dimension. In the second dimension also there is a gap of 2, right. Now, let us see, there was one message which would have come with timestamp 3, right. Now, that has also not been received. There was some message which P2 had broadcast with its own dimension as 3, P3 has not yet received that. So, it is still at 2, right, all right. And the next one is this one, okay. So, if you receive the message, if you receive a message from Pi, like we saw just now, if there is a message which is received from Pi and it is received by Pj, then what are the things that we should check? One is that in the ith dimension, what is I? The sender. In the ith dimension, what should we check? Whether Pj, the Cj I, sorry, Cj I should be, we will not deliver until Cj I is, yes, the vector timestamp of message M, this is my message M in the ith dimension minus 1, right, and for all others it should be okay, for all k not equal to I. Now, is it clear why the ith dimension is being treated separately? Because the message is coming from the ith dimension. So, it has just incremented this from 3 to 4 and send it to me. So, the only message that I have not received here is the one which had timestamp 3 from J, from P2, okay. From P2, the message which was timestamped by 3 by P2, that has not reached, but this is the next one because it is timestamped with 4. So, there has to be a gap of exactly 1. For the other ones, I cannot deliver until I actually update them to their respective values, right. But no problem if this is larger. Suppose instead of 4 to 8, this was 6 to 8. What does that mean? That means that P1 has delivered 6 messages, right, and P2 has still not received one of them. Okay. Now, that may not be a problem in delivery, because it may so happen that P2's delivery of this message happened before P1's delivery of this message. Finally, when m is delivered at j, Cj is updated according to the vector clock rule. All right.
In that case, the example will be updated, like only the second dimension will get updated. The example is true.
In the example here, this one, yes, when this one gets updated, when we update this with this message, we will take the max of all the dimensions, right. So, max of all the dimensions will be 6, 4, 8, but see, we will not deliver it right now. So, this updation will not happen right now. When will it happen? When the message m is delivered at j, okay, then we will update Cj. So, what does that mean? That suppose from P2 you got the message 5, 4, 7, right, and here your thing was 4 to 8. The delivery of this message will be held up until the previous messages come. So, for example, let us say now that I get another message from, this is P3, I get a message from P1 with okay. Now, are we going to deliver it? This is M1, this is M2. Will we deliver M2? Not yet, right? Because this is still, there is still a gap of 1 here. This is 3, this is 2. No, but see, look at the first dimension. In the first dimension, sorry, I wrote this wrong. Just let me rewrite it. This is 3, this is 3. So, in this dimension, okay, oops, just yeah. If it is 5, 3, 6, what are we going to do about it? Shall we deliver M2? See, in when P3 receives this from this one, right, it sees that the first dimension is okay, it is 1 less, its own dimension is 1 less. So, that satisfies the required criteria, but in P2 it shows that this is 2, this is 3. Okay. So, the message that was sent by P2 time stamped with 3 has not yet arrived, but P1 was aware of it. So, that message causally precedes this one. Now, suppose from P2 you get a message which has 5, 3, 6, sorry, 5, 3, 6, yeah, that is right. Now, what are you going to do? This is M3, Now we will deliver this one, right. We will deliver this one because in the second dimension there is a difference of 1, and in the other dimensions, oh sorry, this won't be 4, this will be 4, because you see this can't be 5, because this, when this message was sent, at that time this message was already received, right. So this has to be less than this. So 436, let us say. When you get this, then you see this dimension is equal, this is 1 more, and this is greater, right. So it satisfies the requirement for the delivery. So M3 is delivered first, and what do we store in the, how do we update the clock? The vector clock will be updated to the maximum 4, 3, 8, right. Now let us see, it satisfies the delivery requirement for M2, max, huh? Okay. So now the delivery requirement for M2 is satisfied, because it is 1 more in the first dimension, this is sent by P1, and the in the remaining dimensions this is as large as the timestamp. So now M1 will be delivered, M2 will be delivered, okay. And what will be the updated clock now? 5, 3, 8. Now look at the M1, the delivery requirement of M1 is now satisfied. This is received from P2, and in the second dimension this is just 1 more, and in the other dimensions this is as large as this timestamp, right. So now M3 will be delivered, and the timestamp will become sorry, this is M1, right. M1 will be delivered, and the timestamp will be 5, 4, 8. Okay, right. Now see, it is very important to note that the timestamp grows in the, I mean every subsequent timestamp is larger than the previous one, right. So that's how it should be. So 438, then 538, then 548, right. So though the messages were received in M1, M2, then M3, actually they are delivered M3 first, then M2, then M1. We are not updating clocks when we receive it, we are updating the clocks when we are delivering the message, delivering it up the network stack, delivering it to the application layer. See, the updation of the clock took place here. Here my clock was 428, I got 547, I did not do anything, I just held back M1. Then I got M2, it was 536, again it did not satisfy the requirement for delivery, okay. So I held it back. Then I got M3, and M3 satisfied the requirement for delivery. What requirement? The first, that in the, it is received from P2, so in the second dimension this timestamp is 1 more than this, and in the other dimensions P3 is updated in the sense that it has values as large as that shown on the timestamp. So therefore we know that M3 can be delivered, M3 is delivered, here the clock is updated, okay, and updated to the max of this and this. No +1 business here, because we are only counting send events, right. So max of these two is 4, 3, 8, and then when we arrive at this value of the clock, now it satisfies the delivery requirement for M2. So, we deliver M2 and then again update the clock by comparing, taking the max of these two, right. And then again we see that given that this is the value of the clock, it satisfies the delivery requirement for M1. So, M1 is delivered and this is the final value of the clock.
So what if more than one message satisfies the condition?
More than one message will not satisfy the condition.
Suppose for M1 547, if it is 447.
If this is 447,
Then after M3 is delivered, both M1 and M2 satisfy.
if it is 447 after M3 is delivered,
It cannot be 5 because M1 causally precedes M3 and this is 5 and that is 4.
which causally precedes which one?
M1 and M3.
M3 causally precedes M1.
No, M3 is seen later.
This is later but delivered earlier. So, M3 causally precedes M1.
Suppose M1 is 447.
If M1 is 447, so let us try to see this question, that if M1 is 447, yes, then
Up to M3 is the same thing.
let us go through this. It still, it does not satisfy the delivery requirement here, okay. No, it does not satisfy because there is a gap of 2 here, right. Now you get 536, right, fine, you get 536. Does it satisfy this requirement? No, okay. Now 536, okay. Now you get this 436, right. Now for 436, okay, now this is okay, this is okay, this is okay, right. Now we deliver this, right, and it becomes 438, yes.
Now both satisfy, both M1 and M2 satisfy.
Yeah, so let us see, this is M1 has 4. Now you are saying that at this time M1 is satisfied.
4 is greater than or equal to 4, 3 is less than 4, 8 is greater than or equal to 4.
This is P2, okay. So for this is satisfied, and for 536 also it is satisfied. Yeah, so then I think these two are concurrent ones. It must be the case that we have 447, 536, right. So they are concurrent. 447 and 536 are concurrent, because this is not less than this is not less than this, right. So you can deliver them in these two in any order, right. Okay, so I was hoping to start on the global state recording algorithm today, but I think we have run mostly out of time. Let me just give you the idea of what we want to do. Okay, just before we go into that, let us just look at some issues with the vector clock. Now, the problems that are there with vector clocks is that message size increases since each message needs to be tagged with the vector, and the size can be reduced in some cases by only sending values that have changed. The next topic that we will look at is global state recording. So the problem there is that you remember that in one of the earlier classes we discussed the problem that there are continuously different kinds of activities going on in the distributed system, like transactions in a distributed database, and then if we want to record the global state of the system, like the total balance of the branches in a bank, then it is non-trivial to do that, because when you are recording the state of one one component of the system, it may have already sent some messages, and those messages may have been received on the other side before you record the state of that side. So, because there can be messages in transit, it is possible that the state that you record is not correct. For example, you remember that we were talking about the transfer of rupees some amount A, let us say rupees 10,000 from X account X to account Y, and if we do X equal to X minus Y, X minus 10,000, right, and then the message that asks Y to add 10,000 is on the way, right, and let us say that before it reaches we have recorded the state of X and we have recorded the state of Y. Now, this is not a valid global state. Why? Because we will see that the total balance here is 10,000 less, right. So, when we want to record the global state of the system, we have to somehow think of a state where there is nothing in the channels. The channels are empty and you have recorded the state of all the nodes, right. But in reality you can never achieve that. You cannot stop the system and say that let us stop the system, suspend all activities and then let the messages get delivered, then I will record the global state. That will destroy concurrency to a large extent. So, we want to record the global state without stopping the system, right. So, there has to be a mechanism by which we record the state of the nodes and the state of the channels without interfering with the actual computation. Okay. That is one problem that we are going to study in the next class, and the other problem that we are going to study is that of termination detection. See, a lot of distributed algorithms that we will see from time to time, the computation is initiated in some node and then the computation spreads to the other nodes. So, one node triggers computation in another node, just like you saw in the routing algorithms, that whenever a new node comes up, it broadcasts its routing table to its neighbors, the neighbors recompute their distances, then if some distance has changed, then they transmit their routing tables to their neighbors, and that is how the thing starts spreading. Now, when will you decide or when will you conclude that this computation has terminated, right, because it is not happening in one place, it is happening in n number of places. So, when do we know that the system has stabilized and there is no more perturbations, no more changes or no more part of the computation still active in any of the nodes, right. That is the termination detection problem. So, we will see that we can piggyback the algorithms with certain other types of messages to detect when termination has taken place. So, this is not a separate algorithm on its own, it is an algorithm, it is a trick which is used by the algorithm designer for distributed algorithm on top of the existing algorithm to detect when the algorithm has terminated. Okay. These are the two things that we are going to study in the next class.